The Golden Gate Bridge, the landmark of San Francisco, an architectural masterpiece. Its construction was nothing less than a technical miracle.
To build such a large bridge over the open sea in an area that is earthquake-prone was an unimaginable risk.
It is the most famous bridge in the world, a genuine legend. But what happens when this legend meets a modern-day icon? The Golden Gate Bridge faces the Millau Viaduct, a bridge of superlatives. Higher than the Eiffel Tower, longer than the Champs-Élysées, and it looks simply breathtaking.
It is truly amazing how such a colossus can appear graceful and almost weightless.
The bridge seems to float above the clouds. The Millau Viaduct, like the Golden Gate Bridge, is considered a marvel of architecture. A contest of superlatives, 2 opponents, 3 categories, and lots of surprises. Design. Which bridge has the most groundbreaking design? Construction. How difficult was it to build the gigantic structures? And effectiveness. How do the bridges compete in practice? We are about to find out in Legends versus Modern Icons. San Francisco, once the city of gold diggers and hippies. Today, it's one of the most important locations for the tech industry. But the metropolis is famous above all for the Golden Gate Bridge. Opened in May 1937. Spanning 1,280 meters, it held the record for an impressive 27 years. At 227 meters tall, it is more than huge. The Golden Gate Bridge is gigantic. Its deck is suspended from 500 vertical ropes. In turn, these hang from the world's thickest and longest support cables. More than 80,000 tons of steel and around 700,000 tons of concrete were used to build this colossus. And all constructed in just 4 years. A revolution in the history of bridge architecture.
It was not one record, there were several. Actually, everything about the Golden Gate Bridge was sensational.
But how does the more than 80-year-old legend compare with an icon of the 21st century? In December 2004, in the French Massif Central, British star architect Norman Foster created nothing less than a superlative structure. The Millau Viaduct. At a length totaling 2,460 meters, it eclipses any of the world's cable-stayed bridges. Its height rises up to 343 meters. The Millau Viaduct is the tallest bridge in the world. 154 stays, directly attached to 7 pylons, support the bridge deck. In total, the Millau Viaduct contains more than 36,000 tons of steel and 200,000 tons of concrete. Construction time took just 3 years.
Both bridges are definitely among the most magnificent constructions in the world. Which one is the most impressive? We will see.
Millau Viaduct versus Golden Gate Bridge. The contest begins. The first main category, design. To begin, which bridge is more technically innovative? At the beginning of the 20th century, San Francisco was booming and bursting at the seams. The problem, the city is located on a peninsula. New housing space was therefore scarce.
Hardly any other American city grew so fast at the time, and yet had so little room into which it could expand.
To the north are the sparsely populated areas of Marin Peninsula, but in between is the Golden Gate Strait. To create new housing space, a bridge was needed. But to build a bridge of such dimensions was considered impossible by most people. Nevertheless, a group of bold engineers dared to attempt it. Their biggest challenge was the enormous span. The strait is 1.5 kilometers wide, and the water is deep. The only way for the engineers to do this was to build a suspension bridge, because the number of piers had to be minimized in order not to impair the frequent shipping traffic.
The largest spans can be overcome with suspension bridges, but at the time no one had ever dared to do one at that size. Would the proven technology work at a scale of 1 kilometer?
The design was considered radical and was based on a new theory. Bridges over extreme span widths should have a self-stabilizing effect due to their higher weight. They are not rigid, but can sway in the wind and deflect under loads. Engineers could therefore plan for fewer bracing elements below the bridge deck, thereby also saving costs. Suspension bridges must be both stable and flexible, within precisely defined limits. Otherwise, they might collapse.
Calculating the dimensions of the elements correctly was incredibly complicated. The static analysis filled up 10.5 volumes, considering that everything was done without a computer.
The Golden Gate Bridge could sway up to 8 meters in the wind. When fully loaded, the deck could sag 5 meters. Only in this way was it possible to build what was then the world's longest suspension bridge. A balancing act where each detail determined whether it would hold. The U.S.-American design, as innovative as it was daring. How daring were the French engineers? The Tarn River's impressive gorges in the south of France are hundreds of meters deep. The austere landscape is mainly limestone, not exactly the best conditions for a bridge. But the valleys were also a bottleneck for long-distance traffic. Congestion and accidents were frequent, especially during holiday periods. For more than 20 years, experts had been sounding out the terrain to overcome the problem. Their solution? A cable-stayed bridge, in which the stays run directly from the towers to the deck. But this newer type of bridge has never before been built in such gigantic dimensions. It stretches from plateau to plateau, with a total length of 2.5 kilometers.
When engineer Michel Villaugeux presented his plans, everyone thought he was crazy.
The 7 bridge piers, including pylons, were to be as tall as skyscrapers, up to 343 meters. The problem, on the one hand, the piers needed to be very wide and rigid to withstand the enormous forces acting on them. But the bridge deck would expand by more than 0.5 meter in heat. So, on the other hand, the piers needed to be flexible enough to cope with such expansion. The ingenious solution was to split the piers at their upper end into a Y shape. They would then be rigid at the bottom and flexible at the top.
The piers are reminiscent of a tuning fork. This form is technically and aesthetically ingenious.
Based on these innovative plans, the architects and engineers created the tallest and longest cable-stayed bridge in the world. Verdict in round 1. The builders of both bridges took tried and tested structure types to the extremes. New theories and unusual techniques enabled their constructions to exceed every dimension. But that's not all. Nobody would want an unsightly bridge monstrosity as a landmark. Which design is more impressive? Incredible as it sounds, the first plan for the Golden Gate Bridge was considered an absolute aesthetic catastrophe. The combination of suspension bridge and cantilever truss was, to put it mildly, anything other than elegant.
Chief Engineer Strauss designed a steel monster. People found it ugly and depressing.
But fortunately, consulting engineer Leon Moisseiff had a completely different vision up his sleeve. He reduced the stiffening girders to a minimum. The new design then looked slim and elegant. Together with architect Irving Morrow, he planned to turn the Golden Gate Bridge into the world's biggest Art Deco sculpture. Art Deco was the predominant style of the Roaring '20s. As the economies of the victorious powers of the First World War boomed, people believed in a better future through technological progress. Emerging in Paris, Art Deco conquered the world, also influencing the architecture of American cities. Elegant forms with clear geometry, premium materials, sensual elements, and strong colors characterize the style. Typical decorations include arches, steps, angles, and jagged lines. The final design of the Golden Gate Bridge was ultimately based on this model.
Morrow's design has ensured that the Golden Gate Bridge is still a true legend today.
More than anything else, Morrow redefined the proportions and shape of the towers. They rise like ladders up into the sky. Chevron cladding covers the tower's lateral bracing. The result is the largest Art Deco bridge in the world. For lighting the pedestrian sidewalks, Morrow opted for low-pressure sodium vapor lamps that emit a soft amber light. Lamps pointing upwards also emphasize the extreme heights of the towers. Only one problem remained, and that was not exactly minor. What color should the bridge be?
There was huge controversy at the time. Some people wanted the bridge to be grey so that it would stand out as little as possible, but the Navy wanted it to be particularly visible because of low-flying aircraft.
The Navy actually wanted to paint the Golden Gate Bridge black and yellow, now unimaginable from today's perspective. Fortunately, Morrow finally got his way and coated the bridge in the rust protection paint International Orange.
The color picks up the earth tones of the San Francisco hills, and at the same time forms a brilliant contrast to the blue of the sky and of the sea.
The legend among bridges certainly has a unique aesthetic, both beautiful and graceful. A bridge like a work of art. What does the modern icon have to compete? In the south of France, the Briton Sir Norman Foster, a superstar in the world of architecture, faced an enormous challenge.
His declared goal was that despite its scale, the Millau Viaduct should be as delicate and transparent as a butterfly.
Cable-stayed bridges are inherently more slimline and elegant than other types of bridges. And because the bridge piers need to be extremely stable, the deck can be particularly flat.
Considering the size and scale of the construction, it's amazing how refined it actually looks.
Foster also focused on achieving the greatest possible symmetry. The Y shape was actually only important for the statics of the outermost piers, but the architect insisted that every pier took this form. Above the bridge deck, the design then continues with the Y-shaped pier form and literally turns it upside down. The piers and pylons then appear as a single unit. The bridge is as high as a skyscraper, while being as graceful as the mast of a sailing ship. The lighting concept underlines this special structural feature, the mirroring of the piers and pylons. In choosing colors, Foster focused on light tones. The bridge should merge with the sky and appear transparent and weightless.
He wanted the bridge to be as delicate as a butterfly, and he succeeded. The Millau Viaduct is one of the lightest and slimmest bridges in the world.
Everyone was enthusiastic about the design, whether locals, travelers, or international specialists. Both icon and legend are aesthetic masterpieces that blend perfectly into their landscapes and are simply timeless. So far, a contest of equals. But now we turn to the vital aspect of stability. How do the bridge designs defy the forces of nature? This was a matter of life and death in constructing the Golden Gate Bridge. The San Andreas Fault is just 11 kilometers away, where the Pacific and North American plates meet. Extreme earthquakes are a constant threat.
For the people of California, it's not a question of if, but when the next major quake will occur.
This fact caused headaches for the engineers of the Golden Gate Bridge, since their bridge had to withstand the next quake. The plan: to build huge anchorages, each weighing 60,000 tons. The foundations of the piers were estimated at 18,000 cubic meters of concrete. The tower design also intended to prevent a catastrophe by using a newly patented innovation. The beams had a honeycomb structure. These were to make them both lightweight and stable.
For a long time, it was believed that the Golden Gate Bridge could withstand earthquakes of extremely high magnitudes thanks to these measures, but nobody knew for sure.
Years went by with the ground often moving, but only to a lesser extent. While San Francisco was in fear year after year, a disaster of a different kind happens more than 1,000 kilometers further north. The Tacoma Narrows Bridge, with a span of 850 meters, was the third longest bridge in the world at the time. But just a few days after opening in 1940, it had to close again. And a few months later, the brand new structure collapses. The cause is a mere moderately strong wind. The reason? Its slender design.
The elegant shape was the downfall of the Tacoma Narrows Bridge. Its proportions, lack of stiffening, and aerodynamically unfavorable shape made it flexible and susceptible to dangerous twisting and torsional motions.
The precarious one. The builder of the Tacoma Narrows Bridge was Leon Moisseiff, the chief engineer of the Golden Gate Bridge. A few years later, its deck was to be stiffened to stay on the safe side. This was to provide additional protection from strong winds. But what about earthquake safety? This was tested. On October the 17th, 1989, the ground moved for only 15 seconds, but the quake still caused damage costing millions and claimed 62 lives. Part of the Bay Bridge in western San Francisco collapsed. Like the Golden Gate Bridge, it was a suspension bridge, built almost at the same time. But the legend defied the quake. The Golden Gate Bridge remained standing. But for how long? Doubts remain.
In this earthquake, the epicenter was relatively far away, about 100 kilometers. But what if the next earthquake had a closer epicenter?
Results from scientific simulations were disturbing. In stronger quakes, a collapse was possible. Numerous modifications and the installation of shock absorbers were to make the Golden Gate Bridge even safer for the future.
Ultimately, the seismic retrofit of the bridge has cost to date over $900 million, and it's not even completed.
Nevertheless, the Golden Gate Bridge withstood the biggest earthquake disaster in its history with distinction. How does the modern icon cope with natural catastrophes? Although earthquakes are not a major hazard in this region of France, storm force winds are.
The Millau Viaduct is located in the main wind direction, and the forces trying to push it over on the road deck can be very extreme.
In a worst case, extreme winds could simply tear away the steel deck. The engineers had to come up with something to prevent this from happening. The solution? A 1 meter 20 gap between the piers and deck. An aerodynamic design speeds up winds below the roadway support, creating a downforce. Rounded edges also improve aerodynamics. Engineers first tested a model of the Millau Viaduct in a wind tunnel, until they were confident that even storms of 205 kilometers per hour would have no effect on the bridge.
Compared to the construction of the Golden Gate Bridge, people today have a completely different understanding of the aerodynamic effects around the bridge.
3-meter-high windbreaks also protect vehicles on the roadway. All in all, a complete success. The bridge has never had to close due to storms. The modern icon defies the forces of nature. In contrast, engineers at the Golden Gate Bridge had to make several improvements. The verdict on design. The legend impresses on aesthetics. The modern icon on safety. Both are technically innovative in equal measure. What about the second category? Next up, the construction phase. Which project had the bigger problems to overcome? How difficult was it to build such gigantic structures? Like almost any large-scale construction project, the Golden Gate Bridge also had to struggle with opposition even before the groundbreaking ceremony. Around the Golden Gate, the landscape is classed as unspoiled and of outstanding natural beauty. Many believe that such a massive bridge would destroy the San Francisco's aura. There were also economic aspects. Local shipping companies feared that the bridge would interfere with traffic and thus ruin their businesses. Ferry operators were also concerned about business. In more than 2,000 court cases, they attempted to defend their lucrative monopoly. And even the Navy opposed the bridge. They feared it could be collapsed by enemy bombing, blocking entrance to the port.
Chief Engineer Strauss had to do an incredible amount of persuasion. He personally went everywhere to promote his bridge.
Strauss was successful. In 1930, permission had been granted for a bridge over the Golden Gate Strait. But the next problem was looming. Because in the previous year, Wall Street had collapsed, and with the stock market crash, the Great Depression had begun. The financial crisis gradually spread throughout the country. Under these conditions, not many had the courage to invest in such a gigantic building.
Never before was there so much turnover in the construction process that was nevertheless finally completed. The people of San Francisco, at times of crisis, said, "We will foot the bill," and they did.
People even put up their homes as collateral for a $35 million bond issue, the amount of the budgeted construction costs. Adjusted for inflation, that would be more than $600 million today. It was only due to this action that after 20 years of planning, construction work finally began in 1933. In spite of all opposition, the legend was finally to make history. Around 100 years later, the engineers of the Millau Viaduct struggled with similar problems. Residents protested because many believed that the gigantic dimensions of the bridge would simply blight the breathtaking landscape in the heart of France.
Many locals saw Foster's architecture as a megalomaniac project.
Many were also critical of the high construction costs. And again, the world went into a financial crisis shortly before construction began. First, investors were worried about the so-called Year 2K bug. Many believed that computer systems would crash due to the turn of the millennium. Then, in March 2000, the dot-com bubble burst. Many hyped-up tech companies were unable to meet their profit expectations. Share prices collapsed worldwide. Nevertheless, politicians in Paris gave the go-ahead to build a new national icon.
The state finally commissioned the descendants of Gustav Eiffel, the builder of the legendary Eiffel Tower, to build the Millau Viaduct.
On the 14th of December 2001, the construction company Eiffage finally laid the foundation stone. They were to bear the construction costs of around 400 million euros, the equivalent of more than $600 today. In return, Eiffage received the right to collect tolls for 75 years. Both gigantic projects met with massive opposition, both then and now. It took years to overcome them, but ultimately the foundation stones were laid, to then face the next major challenge shortly afterwards: construction of the bridge piers, the tallest of their time. At the Golden Gate Bridge, erecting the northern tower was a minor task because of the shallow water. On the south side, in contrast, it was a major challenge due to water depths of 33 meters.
Never before has a bridge pier been built at this depth and in the open sea. For many, it sounded crazy.
The solution? Engineers used underwater bombs to level the rocky seabed. Divers then installed a steel frame for pouring in the concrete. It was called a fender and was the size of a football pitch. Its 12-meter thick walls not only enabled the foundations to be laid, it was also intended to protect the piers from any kind of later hazard. For the divers, strong currents were a huge risk.
Because of the currents, divers can only dive during the tide change, 4 times a day for 20 minutes.
There was hardly any time to undergo decompression. They faced a constant threat of respiratory distress, internal bleeding, and unconsciousness. The fender was finally in place. As soon as it was pumped dry, the laying of the foundations could begin.
It took 2 years to lay the foundation of the South Pier. Crazy when you consider the entire construction of the Golden Gate Bridge took only 4 years.
The rest of the substructure was comparatively simple. Within 6 months, prefabricated hollow steel cells and around 1 million rivets were used to create the tallest bridge towers of their time. Foundation work on the Golden Gate Bridge's South Tower was one of the most difficult in history. Was construction of the Millau Viaduct substructure even more complicated? None of the 7 piers is submerged in water, let alone in the sea. But the limestone below is porous and full of cavities. The risk of landslides is ever present.
Ensuring a stable foundation here is no easy task.
To ensure the piers are sufficiently stable, each of them stands on 4 board piles up to 15 meters deep.
Despite the poor soil, it took the builders just 6 months to construct all the foundations. When compared to the Golden Gate Bridge, where everything had to be done underwater, they were much faster.
But the foundations were not the engineers' only problem. They were also concerned about the pier's complex geometry. At the base, the diamond-shaped piers have a cross-section of 200 square meters. Towards the top, they gradually reduce to an area of about 30 square meters. As a result, concrete formwork was extremely complex and required constant adaptation to the required form.
Every 4 meters, the climbing formwork had to be adjusted and repositioned within a tolerance of few millimeters.
Each pier needed to end precisely at a specified point, hundreds of meters above the ground. The taller the pier, the greater the likelihood of error. To overcome this problem, engineers used the Global Positioning System, GPS, for the first time in bridge construction. We all now use this technology in our mobile phones and sat-navs to determine locations. The principle behind it, a receiver detects signals from at least 4 satellites and calculates the exact position from the difference between the signal paths.
The whole thing works with a precision of 10 meters. Good enough for road traffic, but for the construction of a bridge, even an error of 10 centimeters would be a disaster.
Even the slightest movement caused by temperature fluctuations or vibrations raised the risk of misalignment.
The same project would not have been possible even 20 years earlier because the technical innovations did not yet exist.
After about 20 months, the engineers breathed a sigh of relief. They completed the construction of the world's tallest bridge piers. Verdict: constructing the piers was a challenge in both projects. Builders of the Millau Viaduct primarily needed state-of-the-art technology. Builders of the Golden Gate Bridge had to risk their lives. Round 3 concerns the superstructure. How complicated was it to install the bridge decks, including support systems? For the Golden Gate Bridge in the mid-1930s, the primary requirement was gigantic cables. The bridge builders were treading new ground. They needed the world's longest cables at 2,332 meters and at a diameter of 92 centimeters, also the thickest. Their weight, 12,000 tons per cable.
At the time, it was impossible to pull such heavy and long cables over the more than 200-meter high pylons. They had to assemble them on the spot, so to speak.
Wheels transported individual wires from anchor block to anchor block. Only then were the individual wires spun together to form a main cable. Strenuous work. Each cable is made up of around 27,000 individual wires.
This still relatively new air spinning method made suspension bridges of this span possible in the first place.
And the method was enormously efficient. Progress on the Golden Gate Bridge was shortened by a whole 8 months. The longest suspension bridge in the world at the time was therefore built at breathtaking speed. In the 21st century, engineers of the Millau Viaduct were faced with a similar challenge. How do you install a bridge deck 2.4 kilometers long, weighing 36,000 tons, and at a height of 245 meters?
Normally, the deck is built cantilevering out from the pylons step by step, but this wasn't possible in this case.
The force of the wind alone at this height made installation in the open air almost impossible. The construction company Eiffage, therefore, planned to pre-assemble the bridge deck elements on the 2 plateaus. That meant on safe ground. And from there, they were pushed over each bridge pier to the middle.
But even this proposal was gutsy. No one had ever attempted to do it on this scale before, but it seemed to be the only feasible way to complete the project.
To prevent the piers from collapsing, frictional forces need to be kept as low as possible. Engineers therefore installed Teflon-coated wedges at all support points. The launching system was to repeatedly raise the bridge deck, push it forwards by 60 centimeters in 4 minutes, and then lower it again.
No one could say for sure if this would work. On the contrary, many people doubted that it would work.
At first, everything ran smoothly, but after 6 months, a problem suddenly arose. One of the Teflon coatings ripped and the system blocked. The bridge deck hung unsecured in the air. 245 meters above the ground. The weather forecast also predicted storms.
It's hard to imagine what the responsible engineers went through.
After nerve-wracking hours, they managed to replace the broken Teflon on the next morning. Finally, they could push the deck forwards again. But only at the end would they know whether the two deck sections really would align perfectly. The curved road surface and height differences on both sides made it an extremely complex venture. After 1 year and 2 months, the big moment arrived. The two sections met, and they aligned.
The relief must have been enormous. The deviation was less than 2 centimeters, which was within tolerance. Only now is it clear to everyone they'd made it.
The engineers of the Millau Viaduct accomplished their technical masterpiece with aplomb. And it was probably more complex than the spinning of cables at the Golden Gate Bridge. The verdict in the category construction. Both bridges had major hurdles to overcome, whether in terms of permits, foundations, or superstructure. Now for the final, effectiveness. How do the bridges compete in practice? In 1930, 41,000 people lived in the north-located Marin County. Many of them worked in San Francisco. Every day they crossed the Golden Gate Strait by ferry. Waiting times of 2 to 3 hours were not uncommon. And even at weekends, the ferry service reached its capacity. The reason? Cars were becoming increasingly popular. At weekends, more and more people from San Francisco were taking car trips out to Marin County to enjoy the unique landscape.
The Golden Gate Bridge gave the people of San Francisco immediate access to the surrounding area of Marin County.
Then, in 1937, the Golden Gate Bridge was completed. On the 28th of May, none other than U.S. President Franklin D. Roosevelt opened it by the push of a telegraph button. 32,000 motor vehicles rolled over the bridge on the first day, a massive number for the time, and the traffic kept increasing.
The Golden Gate Bridge had a massive impact on the entire region. The population of Marin County increased fourfold within 30 years after construction.
Today, thanks to its 6 lanes, the Golden Gate Bridge enables 120,000 travelers and commuters daily, around 40 million a year, to reach their destinations. To efficiently manage this massive traffic, the Golden Gate Bridge is using a zipper machine. In peak times, it can move lane barriers.
These measures are far from sufficient. The bridge was designed for a capacity of 9,000 cars per hour, but during rush hour, this number reaches 11,000.
The world's most legendary bridge has ensured rapid growth. In traffic management, however, it is often on the verge of collapse. What about the effectiveness of the modern icon, the Millau Viaduct? Before its opening, every vehicle here struggled along serpentine roads. In the valley, it was necessary to cross the River Tarn over a narrow ancient bridge, and then drive back up again. This resulted in kilometer-long traffic jams. Especially during the holiday season, everyone associated the small town of Millau with traffic hell.
Motorway number 75, an important link between northern and southern Europe, was interrupted here. In summer, some of the worst traffic jams in Europe regularly occurred here.
Then, on the 14th of December 2004, the French President Jacques Chirac himself opened the Millau Viaduct. Traffic volumes are nothing compared with San Francisco. An average of just 15,000 vehicles cross the world's tallest bridge every day. At peak travel times, this number can, however, reach as much as 50,000.
As skeptical as the people in the region were about the construction of the bridge, they're the ones who have benefited greatly.
Economically, the bridge has been a success. With its construction, visitor numbers to the once structurally weak region are soaring. Both bridges are blessings for their regions. They revolutionized traffic and boosted economies. But year by year, the Golden Gate Bridge is reaching its limits. But bridges are not just about getting from A to B. They are also landmarks for their regions and attract masses of visitors. Which bridge has the greater cult status? And this round, the Golden Gate Bridge has been performing powerfully from day one. On Pedestrian Day, 200,000 people came to make a claim on their new architectural wonder. San Francisco's population immediately fell in love with their bridge. The city government lured the big movie stars of Hollywood and thereby promoted the bridge's cult status.
Film productions receive favorable conditions. Hitchcock's Vertigo, Planet of the Apes, Star Trek, James Bond, hardly any other setting appears in more movies.
And year after year, more and more tourists came. Around 10 million a year now come to see the most famous bridge in the world. One thing is certain, the Golden Gate Bridge's cult status has remained undiminished since its construction. It is the landmark of San Francisco and the entire West Coast. Not for nothing is it the most photographed bridge in the world. A tougher contender is hard to imagine. But the Millau Viaduct is now also visited by almost 1.5 million people every year, who include tourists, architects, and bridge enthusiasts. At the beginning, many fans even stopped halfway along the bridge to admire the structure. This is now forbidden. Wherever it can, France has also been promoting its magnificent structure, the tallest in the country.
The French are extremely proud of their bridge, and they should be. It's one of the most spectacular bridges in the entire world.
But the spectacular bridge remains largely unknown outside of France.
Of course, a bridge in this rural, sparsely populated area has more difficulty becoming a cult object.
Verdict. Even when the impressively designed Millau Viaduct certainly stands out in this round, the Golden Gate Bridge is simply unbeatable. It's known by everyone. Time for the very last round. How good were the bridges built? Or in other words, which one is at risk of faster decay? Tons of traffic constantly thundering over the Golden Gate Bridge is as much a strain on it as storm force winds and air humidity. The consequences are huge. A maintenance team of around 40 battle daily against rust and wear. Even in fog, they work their way up to the 200-meter high tower peaks with paint and brush.
The beauty of the Golden Gate Bridge comes with a price. It is a maintenance monster. The everlasting fog and the aggressive saltwater are getting to her.
The bridge's steel is, unlike later bridges, not pre-treated. This makes it particularly prone to maintenance. Every year, bridge workers apply around 19,000 liters of anti-rust paint. Around 20 steel construction workers, known as Sky Cowboys, replace any rusted steel sections or rivets.
This is a brutal job. The storms, the fog, the slippery steel, you have to be made for it.
And the aging lady has other vulnerabilities. Cables and vertical ropes require regular tightening. Temperature fluctuations and stress result in them gradually losing optimal tension. Once in its 80-year history, the bridge team even needed to replace every single vertical rope, all while traffic continued to cross.
The Golden Gate Bridge is so high maintenance that opinion is growing that it should be entirely rebuilt.
Keeping the legend alive really does require an immense effort. How does the modern icon compare? Rust hardly has a chance at the Millau Viaduct. To this day, every component is original. Air dehumidifiers ensure this. The steel is also intensively pre-treated. But it has a different flaw: the porous limestone ground.
The foundations of the bridge piers must be constantly monitored.
State-of-the-art technology is used. The foundations contain 12 fiber optic sensors that detect movements in the micrometer range. At the same time, extensometers at the tips take measurements up to 100 times per second. Despite all the technology, the bridge still needs people too. More precisely, a maintenance team of 4. As with the Golden Gate Bridge, they monitor the tension of the cables. This ranges between 900 and 1,200 tons. The team checks wind conditions every 30 minutes and the temperature of the bridge's deck. They also constantly inspect the piers for concrete damage.
The modern icon is ultimately designed to keep maintenance effort to a minimum.
It has a guaranteed lifetime of 120 years. And it needs much less care than the 80-year-old diva on the Pacific coast. The final category verdict: traffic benefits of both bridges are immense. The legend is vastly superior to the icon in terms of cult status, but it is also much more susceptible to maintenance. Almost 70 years lie between the construction of the Millau Viaduct, the iconic cable-stayed bridge in the heart of France, and the legendary Golden Gate Bridge of San Francisco, the most famous bridge in the world. In terms of design, construction, and effectiveness, both, with their colossal size, bear witness to the pioneering spirit of daring engineers. Both blend perfectly and miraculously into their landscapes, as if they have always belonged there.